in this lesson, we are going to continue from boundary condition. We said boundary condition, these are the support reaction that attach the structure to the ground. The first step you are going to take whenever you want to analyze a building, the first step is you need to determine the support reaction. Okay, because the support reaction, these are what make the structure to be at equilibrium. Let's take a look at an example. Let's say, for example, I'm sitting on a chair, meaning I'm applying a force on the chair, right? In order for me not to fall down, the chair needs to apply an equal and opposite force in order for the forces to be balanced, right? So the chair needs to react by counteracting the force which I'm applying on the chair. So we are also going to use the same concept here. Whenever we are dealing with structural analysis, we need to know that the support reaction, these are what keep the structure at equilibrium. Yes, so we need to first of all determine the support reaction. That is the forces that are going to keep the structure at equilibrium. Like guys, for example, if I start moving around this chair, let's say I'm sitting at the edge of this chair. Guys, the forces won't be balanced anymore, right? Because I'm sitting at the edge of the chair, right? So meaning I can easily fall down from this chair because the chair is not acting, or the chair is not responding with an equal and opposite force. Okay, so I can easily fall down off this chair. Okay, because the forces are not at equilibrium. Okay, so the first step you need to take whenever you want to analyze a building is you first need to determine the support reaction. We are going to discuss pin support, roller support, and fist support. The first support reaction is pin support. Now guys, what is pin support? Pin support, they restrict motion in the S and Y direction. Okay, that is to say, they restrict motion in the S and Y direction and they allow rotation. Now guys, I know you'll be like, so does that mean the structure is going to rotate? No, guys. Actually, the structure is going to deflect a little. And guys, the deflection we are talking about here is like a quarter of an inch, okay? Not like 200 of an inch. No, the deflection we are talking about here is very little deflection. Okay, guys? So this is what we are talking about. So pin support, they are going to restrict motion in the S and Y direction. Okay, so they won't make the structure to move in the S and Y direction. You can see if you take a look at this picture here. So this is the symbol for pin support. As you can see, guys, we have the Fs, which is the force in the S direction, and we have Fy, which is the force in the Y direction. So this is another symbol of pin support. So as you can see, guys, we're having this beam. As you can see, this beam is connected to this other support, or this beam is connected to the other member. As you can see here, guys, so these are examples of pin support. Now guys, the next support we're going to take a look at is roller support. Now guys, roller support, they only restrict motion in the direction of the roller. Okay, so they only restrict motion in the y-axis. Okay guys, so they restrict motion in the direction of the roller. So guys, this is the symbol of roller support, as you can see. So this is only going to resist the motion in the y direction. Now guys, we can also have the roller support like this. As you can see, guys, this is inclined. Okay, so this is inclined to 45 degrees. So if we have a structure like this, the roller support is going to try to restrict the motion in this direction. Okay, so these are the symbols for roller support. So as you can see, guys, if you take a look at this picture, as you can see, this is going to be an example of a roller support. Now guys, when do we have fist and roller support on a structure? Now guys, the common example is going to be a bridge. Okay, in a bridge, we normally have pin support or roller support. Now guys, There is something civil engineers normally do when designing a bridge or when constructing a bridge. There is something we call fixed bearing, and there is something we call tension bearing. So guys, the way civil engineers do this is, we all know that in a bridge we are going to have two supports, right? So civil engineers, they tend to use fixed bearing or tension bearing. Now guys, what is fixed bearing? Now guys, fixed bearing, this is going to be a series of plates that attach the bridge. Okay, so it's going to be a series of plates that attach the bridge to the actual abutment. Okay, to the actual abutment on the ground. This is going to be attached to the abutment. Okay, so this is going to transfer the load to the ground. So civil engineers, they also tend to use tension bearing at the support or on the support, because the tension bearing, this is where we have a slotted hole and the bolt will go through the hole. It will allow it to move a bit. Now guys, why do we do this, or why do civil engineers use tension bearing? Because guys, we all know that from summer to winter or from winter to summer, we have temperature changes, right? So the temperature is going to change from winter to summer, right? And during the change of this temperature, we know that when we get to summer, it is going to be very, very hot, right? So meaning the temperature is going to increase. Now guys, what happens whenever you heat an element? Of course, it is going to expand, right? It is going to expand whenever you heat an element. Now guys, during the stay of a bridge, that is from winter to summer, this bridge, they are going to, so they want to expand because of change of temperature, right? So this bridge, they will tend to expand. And guys, we need we need an element that is going to try to give this bridge the flexibility they need. Okay guys, because if we don't give this bridge the flexibility they need, this can actually affect the abutment of the bridge. And guys, whenever the abutment of a bridge is damaged, this is going to be a very, very big problem. Okay, so we civil engineers, we tend to apply, or we tend to use what we know as tension bearing. So this is going to give the bridge some flexibility they need. Okay, so this is going to try to make this bridge move a bit. Okay guys, so whenever we are in summer, so when this change in temperature try to expand the bridge, so the bridge is going to freely move. Okay guys, so instead of us to have a lot of forces inside the bridge, or instead of us to have a lot of stress inside the bridge, this bridge is going to try to move a bit. Okay, so there's going to be flexibility on the bridge. So this is why civil engineers will use tension bearing at one end of the bridge, and we also use what we know as fixed bearing at the other end of the bridge. Okay guys, so let's take a look at the next, let's take a look at the next support. So the next support we have is fixed support. Now guys, fixed support, they restrict motion and rotation. Okay, so they restrict motion and they also restrict rotation. Okay guys, as you can see guys, we are having Fy, which is the force on the y-axis. We're having Fs, and we're also having the bending moment. Okay guys, so this is going to be fixed. Okay, so it won't allow any movement, so there will be no movement. Now guys, we tend to see this whenever we have a column connected as into the ground, or whenever we have a structure that is connected to the ground. So of course it is going to be fixed, because we don't want the structure to rotate. We don't want the structure to move from one position to another. So we tend to use fixed support whenever we have a structure that's going to be placed on the ground, or whenever we have a column that is going to be connected to the ground. Okay, so as you can see guys, this is an example. As you can see, this is a column. Okay, so this is a column. As you can see, this column is attached to the ground. Okay, so this is what we know as fixed support. So they restrict motion and rotation, so they don't allow any movement. Okay guys, so let's move to the next slide. So now, guys, there is also the potential of internal releases in a structure. Now, guys, this can relieve forces in a given area. Guys, the most common type of internal releases in a structure is what we know as hinge. Okay, guys, so this is what we know as hinge, because what we know about hinge is we know that the bending moment or the moment is going to be equal to 0. Okay, so the moment is going to be equal to 0. Now, guys, if you take a look at this bridge, this is what we know as pin and angle connection. Now, guys, we tend to use hinges whenever we have, that is, whenever we want to transfer a large component, that is a large component, whenever we want to transfer it as into the sides, we tend to use hinge to connect two girders. Okay, so whenever we have two large components, so if we want to try to transport this to the side, so we tend to use hinge to connect these two components. But guys, you are going to find this in most old bridges. Okay, so you are going to find this in most old bridges, because this is usually common whenever we want to connect two girders together. So we tend to use hinges. But guys, the disadvantages of using hinges whenever you want to transfer materials or whenever you want to transfer two girders to the side is whenever this hinge corrode, or whenever there is a damage to this hinge, this is going to lead to a serious problem. Okay, so this is going to lead to a serious problem. So we tend to use what we know as splice element. Okay, so we tend to use what we know as splice element. That is, we are going to have a series of splice with some plates. This is going to connect the components together. As you can see, guys, this is what I'm talking about. So as you can see, we're having series of bolts. Okay, we're having series of bolts connected on the web. Now, guys, in case you don't know, in steel design, this upper part is what we know as the flanges, or this down part is what we know as the flanges, while this middle part is what we know as the web. So guys, we tend to use splices, that is to connect the web together. Okay, so we are going to have some series of bolts with a plate. So this is going to connect these components together. So guys, this is going to give us a more rigid connection. So instead of using hinges, we tend to use splices. Okay, so we are going to use splices with some series of plates. So this is going to connect the two components together. So this tends to give us a rigid connection. Okay, so let's move to the next part. So now, guys, we are going to discuss stability and static determinacy. Now, guys, recall the equation of equilibrium of a 3D system. Now, guys, we are going to be dealing with 2D structure. Okay, so we civil engineers, we always try to deal with 2D structure. Now, guys, this can be reduced to the summation of the forces in the S direction is going to be 0. The summation of the forces in the Y direction is going to be 0, and the summation of the moment is going to be equal to 0. Now, guys, these equations or these are going to be very, very useful when dealing with structural analysis. Okay, so whenever we want to analyze a structure, or whenever we want to analyze a beam or a frame, we are going to be using this equation. Okay, guys, these equations will be critical to performing all type of structural analysis. Okay, like I said earlier, we are going to be using these equations to perform all type of structural analysis. And guys, for example, we will use them to determine support reaction. Now, guys, like I said earlier, the first step when analyzing a building, you need to determine the support reaction. Okay, because the structure needs to be at equilibrium. We don't want our structure to run away from us. We always want our structure to be static. Okay, guys? Now, guys, as you can see, these are the three equations of equilibrium. The summation of the forces in the S direction need to be equal to 0. Summation of the forces in the Y direction need to be equal to 0. And the summation of the moment needs to be equal to 0. Okay? So we're going to be analyzing a beam like this. Okay, guys? but we need to first of all take a look at this. Now guys, in addition, we can use them to determine internal forces in structural elements. Now guys, we're also going to be taking a look at internal forces. Guys, if, for example, I slice a beam into 2 equal parts, we are going to have internal forces that keep this beam static, okay? Guys, these internal forces, these are what we know as axial forces, shear forces, or bending moments. Okay, guys? So these are what keep the beam at equilibrium. We're also going to try to determine the axial forces, the shear forces, and the bending moments. Okay, guys? So we're also going to be dealing with internal forces in structural elements. Okay? Now, for a 2D structure, we have 3 equations of equilibrium. Okay, guys, like I said earlier, so we have 3 equations of equilibrium. Now, guys, when all the forces in a structure can be determined from the equation of equilibrium, then the structure is considered as statically determinate. Now, guys, we're having 3 equations of equilibrium, right? If we have 3 unknown forces, meaning this structure is going to be statically determinate. Okay? Now, guys, if there are more unknowns than equations, the structure is statically indeterminate. If we have more unknowns, that is more unknown forces than the 3 equations of equilibrium, meaning the structure is going to be statically indeterminate. Okay, guys? If there are less unknowns than equations, meaning this structure is going to be unstable. Okay? If we have less unknown than the equation of equilibrium, the structure is going to be unstable. Now, guys, we know that we have 3 equations of equilibrium. So if we have 2 unknown forces, meaning this structure is going to be unstable. Now, guys, you are going to understand this better. So don't worry, guys. I'm going to explain this better in the next slide. And guys, for the majority of this semester or the majority of this course, we will restrict ourselves to structures that are statically determinate. Now, guys, in structural analysis 1, we are going to be dealing with structure that are statically determinate. That is, we are going to be dealing with structure that has 3 unknown forces and 3 equations of equilibrium. Okay? Then in structural analysis 2, we are going to be dealing with statically indeterminate structure. Okay, that is, they are structure that has more unknowns than the equation of equilibrium. Okay, guys, so we have to take it we have to take it one after the other, because you need to learn how to walk before you can run, right? So we are not going to skip the step. We're going to take the step one after the other. So we're going to first of all deal with statically determinate structure. Then in structural analysis 2, we are going to take a look at statically indeterminate structure. Okay, guys? Now, guys, mathematically, this is expressed as follows. Now, guys, we are having a notation here. This is what we know as I sub E. This is what we know as degree of indeterminacy. So, guys, these are external indeterminacy, guys. Now, guys, what do I mean by this? Now, guys, if we have IE, that is I sub E, lesser than 0, meaning the structure is unstable. Okay? Meaning this structure is going to be unstable. Okay, guys? Don't worry, guys. You are going to understand this better very soon. If we have I sub E equal to 0, this structure should be statically determinate. Okay? And if we have I sub E greater than 0, the structure should be statically indeterminate. Now, guys, if you take a look at this equation, we're having I sub E. Okay, I sub E is the degree of indeterminacy. Now, guys, what do we mean by degree of indeterminacy? Now, guys, we said if we have more unknowns than the equation of equilibrium, meaning this is going to be an indeterminate structure. Now, guys, let's say, for example, we have 4 unknowns, that is 4 unknown forces, and normally we always have 3 equations of equilibrium. So meaning this is going to have a degree of indeterminacy to the first power, okay? So we're going to add degree of indeterminacy to the first power, okay? But if we have, like, let's say 5 unknown forces, meaning we are having the degree of indeterminacy to the second power, okay? So this is what we know as degree of indeterminacy. Now, guys, what is arrow? Arrow is the total number of unknown support reaction, okay? So these are the unknown forces. Now, guys, what is E sub C? This is what we know as the total number of equations of condition. Now, guys, E sub C, this is what we know as total number of equation of a condition. In other words, this is what we know as the total number of internal releases, okay? So these internal releases, this is what we know as hinges, okay? So we're also going to determine if the structure is going to have what we know as hinges or not, okay? Now, guys, if you take a look at this yellow box, I said a non-negative value of I sub E doesn't guarantee that a structure is stable, okay? So we will see example of this. So you need to take note of this. A non-negative value of E doesn't guarantee that a structure is stable. Now, guys, you are going to understand this better very soon. So, guys, some examples of different classification of structures. Now, guys, we are going to take a look at this now. Note that since none of these structures have no internal hinges, now, guys, like I said, E sub C, this is going to represent the internal hinge, or the internal hinges in the structure. Now, guys, if you take a look at this theory structure, now, guys, this is a beam, right? So if you take a look at this beam, you're going to find out that we don't have any internal hinge. Now, guys, like I said, whenever we have internal hinge, now, guys, we need to know that the bending moment or the moment at the hinge is always equal to 0, right? So, guys, if you take a look at this, what can we say about this beam? Is this beam stable, unstable, or is this a statically determinate structure? Now, guys, looking at this beam, just looking at this beam, we're going to find out that this is going to be an unstable structure because we are having just 2 roller support, right? If you apply a force on this beam is going to freely deform. Yes, this look like a skateboard. It look like a skateboard because if you apply a force on this beam, it is going to freely deform. So this is what we know as unstable structure, okay? Because if you take a look at the formula, IE is going to be equal to arrow. What is arrow, guys? Arrow is equal to the number of unknown forces. As you can see, guys, we're having 2 unknown forces, right? So meaning this is going to be 2, right? 2 minus, what is E sub C? E sub C is equals to the internal hinges. But, guys, we don't have any internal hinges. So this is equal to 0. Then minus 3, which is the equation of equilibrium. So 2 minus 0 minus 3 is going to give us minus 1. Now, guys, like I said, whenever we have I sub E equal to, that is whenever we have I sub E lesser than 0, meaning this is what we know as unstable structure, okay? So this is going to be unstable. Now, guys, if you take a look at this other structure or this other beam, you're going to find out that we're having 3 unknown forces, right? We're having 3 unknown forces, meaning I sub E is going to be equal to 3, which is the arrow, then minus E sub C, which is 0, because we don't have any internal hinge, then minus 3. So 3 minus 0 minus 3 is going to give us 0. Now, guys, because I sub E is equal to 0, meaning this is going to be a stable and statically determinate structure. Okay, guys? So this is what we structural engineers always need. Okay? So we always need to have our structure to be stable and statically determinate. Now, guys, if you take a look at the last structure, we're going to find out that we are having 5 unknown forces, right? We're having 5 unknown forces. So meaning this is going to be 5 minus 0 minus 3. This is equal to 2, right? Now, guys, because I sub E is greater than, greater than 0, meaning this structure is stable. This structure is stable. Yes, it's stable, but it is statically indeterminate to the second degree. Okay, because we are having more unknowns than the equation of equilibrium. Okay, guys, so we are going to be dealing with stable and statically indeterminate structure in structural analysis 2. Okay, so we are going to focus more on stable and statically determinate structure in structural analysis 1. Okay, guys, so let's move to the next slide. Now, guys, a non-negative value of IE doesn't guarantee that a structure is stable. Now guys, what do I mean by this? For a structure to be stable, 3 conditions must be met. Now guys, pay close attention to this. For a structure to be stable, 3 conditions must be met. I sub E must be non-negative, okay? As previously stated, I sub E must be non-negative for the structure to be stable. Also, all the support reactions must be concurrent. Okay, guys, so all the support reaction must be concurrent. Now, guys, what do I mean by this? Now, guys, what do I mean by this? Now, guys, we know that whenever we have a concurrent structure, meaning they all pass through a single point, right? They all pass through a single point. Now, guys, this is supposed to be must not be concurrent. Okay, so this is must not be concurrent. Okay, so guys, we know that whenever we have concurrent structure, meaning the support reaction, they all pass through a single point. Now, guys, if you take a look at this picture, this is a stable structure, right? This is a stable structure. Like men looking at it, it is a stable structure because we're having 4 unknown reactions. But guys, as you can see, these reactions, they are all passing through a single point, right? They are all passing through a single point. Now, guys, if we apply a force on this structure, guys, this structure is going to freely rotate. This looks like a bicycle wheel. Yes, it looks like a bicycle wheel because if we try to apply a force on this structure, this structure is going to freely rotate. Okay, so meaning this is not going to be a stable structure because we are having all the support reaction passing through a single point. Okay, guys. Also, guys, if you take a look at this, okay, let me explain this first. Also, all the support reactions must not be parallel. Now, guys, if you take a look at this, you're going to find out that this beam is having 4 unknown reactions, right? But guys, men looking at it, you might think this is a stable structure. But guys, these are all parallel forces. Yes, these are all parallel forces. If we try to apply a force on this beam, you're going to find out this beam is going to freely deform. It's going to freely move. Because this looks like a skateboard. Okay? Because all the forces are parallel. Okay, guys? So we need to know that all the support reactions must not be parallel. All the support reactions must not be concurrent. And IE must be a non-negative value, okay, in order for the structure to be stable. Okay, guys, so IE must be non-negative. All the support reactions must not be concurrent, and all the support reactions must not be parallel. Okay, guys. Now, guys, for example, the structure as shown, while IE equal to 1 for both structures, they are not restrained to movement. That is think wheel and skateboard. Okay, like I explained earlier. So guys, let's move on. Now guys, keep in mind that internal releases such as hinges, like I said earlier, can also serve to reduce degree of indeterminacy. Now guys, whenever we have hinge in a beam, this is going to reduce the degree of indeterminacy because what do we know about hinges? Now guys, whenever we have hinge or hinges on a beam, we know that the sum of the moment, that is the moment produced at that location, is equal to 0, right? Meaning we now have an additional equation. Okay, so because we now have an additional equation, meaning we are going to reduce the degree of indeterminacy. Okay, guys, so each internal hinges increases E sub C by 1. Now guys, if you take a look at this beam, this is a beam that is indeterminate to the 2nd degree, right? Because we are having more unknowns than the equation of equilibrium, right? So I sub E is equals to 2. But guys, if we introduce hinges inside this beam, now what we're going to have is I sub E is going to be equal to 1 because now we now have 5, right? Because if you take a look at the formula, we know that I sub E, so let me take a look at the formula again. So I sub E is equals to arrow minus EC minus 3, right? So meaning arrow is equal to 5, right? Arrow is equal to 5, which are the support reaction. Then minus E sub C, this is what we know as internal hinges, right? So because we're having one internal hinge here, meaning this is going to be 5, right? This is going to be 5 minus 1, then minus the equation of equilibrium, which is 3. So 5 minus 1 minus 3 is going to give us 1. As you can see, guys, the degree of indeterminacy has reduced from 2 to 1. Okay, so this is the reason we have hinge. So this hinge is going to reduce the degree of indeterminacy. But guys, let's say we apply 2 hinges on this beam. You're going to find out that it is going to reduce the degree of indeterminacy further. Okay, so we are going to have 5 minus 2 because we're having 2 hinges, right? So it's going to be 5 minus 2, then minus 3, which is going to give us 0. Okay, so this is going to be a determinate structure. Okay, guys, so you need to know that hinges, they reduce the degree of indeterminacy. Okay, guys, so this is what you need to know about hinges. Okay, guys, so now this is where we are going to call it. Okay, so in the next lesson, we're going to analyze beam. Okay, guys, so we're going to be analyzing beam in the next lesson. So we're going to be analyzing a structure that is determinate. That is, we are going to be having 3 unknown forces and 3 equations of equilibrium. Okay, guys, so this is what we are going to be discussing in the next lesson. Okay, so in structural analysis 2, we are going to talk about indeterminate structure. Okay, guys, so let's take it one after the other because we need to know how to walk before we can run. Okay, so guys, this is where we are going to call it in this session. So in the next lesson, we are going to determine support reaction. Okay, so these are the forces that keep the structures at equilibrium. Okay, guys, so guys, this is going to be the end of this lesson. If this is the first time you're watching my videos, make sure you click that subscribe button, hit the bell notification icon below, like this video and share this video with your friends. If you don't click that bell notification icon, you won't be notified whenever I upload a new video. And I'm sure you don't want to miss out any video from tutorial. Now guys, in case you don't know, I have a full course on calculus 1 and calculus 2. If there's any of you having problem with calculus 1 and calculus 2 and you are looking for a good course on calculus 1 and calculus 2, click the link in the description box below. You're going to get access to my full course on calculus 1 and calculus 2. The course is very, very cheap. The course costs just $5. Okay, so click the link below to get access to my full course. So guys, this is where we're going to call it. See you everyone. Bye.